Hello, my name is Jessica Mejia. I am a doctoral candidate at the University of South Florida. Today, I am going to discuss how several superglacial lakes that drain rapidly slow sliding speeds at our field site several kilometers down Glacier in the Greenland Ice Sheet. Seasonal variability in the Greenland ice sheet sliding speed is regulated by how its subglacial drainage system responds to meltwater inputs. Early in the melt season, meltwater produced at the ice surface reaches the bed via moulins and crevasses. This meltwater influx to moulins increases subglacial water pressure, reducing basal traction and increasing sliding speeds. Later in the melt season, ice velocities often decrease despite continued meltwater inputs. These velocity decreases have primarily been attributed to the increased efficiency of the subglacial drainage system, where the growth of subglacial conduits is able to drain water from the surrounding distributed system, reducing water pressures and slowing sliding speeds. However, recent observations indicate the drainage of isolated cavities may instead be responsible. When water filled, isolated cavities can produce a lubricating effect at the bed because when sliding slows, pressures can increase above or towards overburden pressure as the cavity contracts around a fixed volume of water. When these cavities are to connect to the distributed drainage system and water is released from storage, this lubricating effect would no longer be present. Currently, the relative importance of isolated cavities versus channels in driving Greenland ice sheet slowdowns is not yet resolved. In this study, we will address this. We set up a field site in the Pacific region of Western Greenland. We established a camp several kilometers down glacier from multiple supraglacial lakes that are known to drain over previous years. So at our field site, we instrumented a moulin so that we could monitor pressures within the most efficient parts of the subglacial drainage system. We also installed 2 GPS units to monitor ice motion. And then in the beginning of 2018, before the melt season started, we installed a seismic station at this camp. We installed the seismic station so that we can measure glacial hydraulic tremor amplitude, a proxy for the subglacial discharge within the most efficient parts of the drainage system. So if we observe changes in sliding speed without similar changes in the efficient drainage system, we can then infer that those changes in sliding are driven by changes outside of the efficient drainage system. Now I am going to go through our time series for the 2018 melt season. In the first panel, we have moulin hydraulic head, then we have tremor amplitude, and then a long flow ice velocity. So the melt season began the first week of June. At this time, sliding speeds increased above wintertime background speeds. As the melt season progressed, we see the onset of diurnal velocity variations, indicating meltwater was reaching the bed and pressurizing the drainage system. In the beginning of July, we were able to instrument the moulin pictured in the last slide. This time series is truncated whenever the moulin water levels fell below our piezometer. Importantly, throughout this entire time period, even when moulin water levels fell below the piezometer's elevation, sliding speeds remained consistently above wintertime background speeds. At the end of July of 2018, we see this increase across our time series, indicative of a lake drainage event. So to confirm this, we checked the satellite imagery. On July 24th, we see that all of the 10 superglacial lakes shown in the study area figure were completely full. Their maximum extents are outlined in red. Then the next available imagery was from July 30th, 6 days later, and all of those lakes had drained completely. Those same outlines are shown. So this confirms that our observations are rapid superglacial lake drainages of Glacier. Now I'm going to zoom you in to the event itself so that you can see the progression of events. The x-axis here is now in hours. So this time series is just over a day long. In the first panel, we have Moulin hydraulic head. In these next three panels, we have GNSS station measurements. So our velocity time series, even though what is shown in the middle panel here only has a 2-hour smoothing average to it, by nature of the velocity calculation itself, it will attenuate the signal. So in the top panel, we show a long flow ice displacement. This allows us to more accurately see the timing of the velocity increase and decrease at the site. And then at the bottom, we have uplift. In the last two panels, we have observations from our seismic station. We have tremor amplitude in blue. Importantly, the tremor amplitude is going to tell us when the flood wave was directly under our study area. Then at the bottom, we have ice quake amplitude. So before 1600 hours or 4 p.m. local time, the ice sheet was exhibiting normal diurnal behavior. At 4 p.m., we see our Moulin head start to increase faster than normal diurnal water level inputs, which are very consistent throughout our entire time series. So this indicates that there was a pressure rise ahead of the flood wave's arrival at our site. As Moulin water levels increased, we see that's when our ice started speeding up, and we see uplift at our site, which is not characteristic of diurnal variability. By 5 p.m., this is when our tremor amplitude says that the flood wave arrived at our site, and peak discharge occurred around 6:15. So the flood wave approach was only about an hour. During this time, we see that Moulin hydraulic head jumped. It was increasing at the fastest rates observed. We see our sliding speeds increase and approach peak event speeds. And we see the fastest rates of uplift observed. Peak discharge past our site was coincident with extremely high Moulin water levels, peak sliding speeds. And at this point, uplift started to increase more slowly. Over the following 2 hours, as the subglacial flood wave started to recede past our site, this is when we see the onset of exceptionally high amplitude ice quakes, unprecedented in our record. Tremor amplitude shows that by 8 p.m., just 2 hours later, most of the floodwaters had drained past our site. This is confirmed because at this time, Moulin water levels are decreasing, ice is slowing down, and uplift is subsiding. Over the next several hours, Moulin water levels gradually subsided and ice speeds decelerated. And by 5:30 a.m. local time the next day, just 7 hours after the flood waters had receded past our site, we see that sliding speeds dropped to wintertime background values for the first time since the beginning of the melt season. This was coincident with still extremely high Moulin water levels. Shown here is the maximum diurnal Moulin water levels over the week before the event, denoting that while we observed the onset of the slowest speed since the beginning of the melt season, Moulin water levels were even higher than they were at their peaks over the week before. At the same time, we see that tremor amplitude was similar to the previous day's value, indicating that the hydraulic capacity of subglacial channels wasn't dramatically increased during the event. This is consistent with modeling work that shows that the timescales for the subglacial flood wave are just too short to induce significant growth of subglacial channels. These observations shows that pressure decreases within the most efficient parts of the subglacial drainage system are not responsible for our observed slowdown. Now I'm going to zoom you into the record so that we can see what happens after the lake drainage event. After diurnal variability resumed, sliding speeds continued to drop to these wintertime background speeds throughout the rest of the melt season. Specifically, over the week before the lake drainage event, diurnal minimum woolen water levels were consistently below the piezometer's elevation. However, during this time, sliding speeds were also consistently above wintertime background speeds. Let me point you to two occasions after the lake drainage event at the beginning of August. So here, woolen water levels are actually above the piezometer. However, now sliding speeds are falling to these winter background speeds. This change in the relationship between diurnal minima indicate that lake drainage induced a persistent basal traction increase. And this basal traction increase is consistent with the dewatering of isolated cavities, since it is not being caused by a reduction in pressures within the efficient drainage system. We envision the progression of events to be as follows. At the beginning of the melt season, meltwater reaches the bed and encounters a drainage system consisting of subglacial conduits and link cavities. However, at this time, the majority of the bed is consisting of isolated cavities that are water filled, producing this lubricating effect whenever pressures drop in the connected system. As the subglacial flood wave approached our site, the most efficient parts of our drainage system were quickly overwhelmed. This drove water out into the distributed drainage system, and high pressures, fast sliding speeds combined to connect isolated cavities. As the flood wave receded past our site, floodwaters would have drained through these new connections back towards the most efficient conductive parts of the drainage system. For the remainder of the melt season, isolated cavities that retained their connection to the distributed system would have maintained pressures below overburden, unlike before the event, thus eliminating their lubricating effect. These results mean that rapid lake drainages can induce slowdowns, despite not being able to increase the efficiency of subglacial channels. Further, shallow surface slopes and the thick ice of the Greenland Ice Sheet make it much different than alpine glaciers. Specifically, this much faster creek closure rates may limit the ability of subglacial channels to lower pressures in the distributed system. On alpine glaciers, subglacial channels can remain open even well past the end of the melt season. This may not be the case in Greenland. The implications for this is that ice dynamics may be more vulnerable to sustained meltwater inputs than previously thought. After the lake drainage event, there were several occasions where sliding speeds remained above wintertime background speeds, and all of these times were correlated with high woolen water levels, meaning that the Greenland ice sheet may be more vulnerable to sustained meltwater inputs than previously thought. Specifically, high overnight meltwater inputs seem to prevent sliding speeds from dropping to these lower values, therefore disallowing the drainage of isolated cavities to offset any speed increases. I would like to thank the organizers for giving me the opportunity to speak, and thank you for your attention. And I would also like to point out talks by my colleagues, one of which was in the same session. Thanks.